There's several problems we can get with only sampling readings. If you've got, for instance, a noisy signal coming in, and you might have a noisy signal for any number of reasons, maybe your signal cable happened to go past a fluoro, or somebody's using a mobile phone next to your sensor, or there's a VSD somewhere within, well, the state, then you're going to get noisy signals. Problems with noise is, if you just have this intermittent noise, with an ADC, because it samples, what can happen is it can pick up a bum reading, and then it holds that reading for the entire sample period. So what a normal system, a normal analog system, would say, oh yeah, it's a bum reading, and just sort of immediately see the next reading and not take any notice. But an ADC going into a PLC will see a bum reading and hold that bum reading for the entire sample period. That is plenty long enough for it to have outputted to a valve. And if it sees a bad reading and outputs to a valve, then the valve will make the system go into oscillation, which means that the whole thing goes silly. Because once we're in oscillation, it's very, very hard to get back out. To get around this problem, we use a thing called a filter factor. I really should have labeled that. It's a filter factor. A filter factor, which is abbreviated to FF. We use filter factors. And what the filter factor does is, instead of just taking the reading through as gospel, the ADC takes a proportion of the last reading, so that if your filter factor is 0.9, it takes 90% of the last reading it had, and then it takes 10% of whatever the ADC is saying right now. So it takes 90% of last reading and 10% of now reading. And that's what is taken and sent through to the PLC. Now that's a lovely thing, because when you use filter factors, the red line here is showing the filtered signal. You end up with beautiful straight lines. The production people love it when we use filter factors, because it looks as if it's beautiful straight lines. The fact is, as soon as we started sampling, we went into the nasty world of statistics. And you probably heard the phrase, there are lies, damned lies, and statistics. As soon as you start sampling, you're into telling lies. Statistics tells lies. PLCs tell lies. If we then use filter factors, we tell even bigger lies. If you have a filter factor of 0.9, then should something catastrophically break, let's supposing we've got a conveyor belt which is transporting stuff from a mine to a mine site. That conveyor belt, just at this point here, broke. The belt snapped and all the stuff starts falling on the ground. With filter factoring, because it takes 90% of the last reading and only 10% of the now reading, it's saying, oh yeah, I had 100 kilograms on that belt. Oh, now I've got nothing. So I'll take 90% of the 100, which is 90, and 10% of nothing, which is nothing. So I'm going to say there's 90 kilograms on that belt. And the next time round, it's going to say, oh yeah, there's 80 odd kilograms on that belt. And there's 65 odd kilograms on that belt. And there's 55 odd kilograms on that belt. So filter factoring is basically lying. It's giving false values at the PLC end of things. And if we have a catastrophic failure, a sudden, immediate failure, the filter factor will say, oh no, everything's fine, the belt's still got stuff on it. And it can actually, if you have a filter factor of 0.9 and you're sampling every, say, 10 seconds, it may be several minutes before the PLC acknowledges the fact that there's nothing actually on the belt. because the filter factoring has smoothed it all away. Now, where this can be extremely embarrassing to an instrument person who put that filter factoring, it can actually be much worse than that, because the next thing that comes along is the accountant. Now, we all know that accountants are idiots. What the accountant will do is he'll look at the PLC reading, and he'll say, oh look, a whole load of stuff went down the belt just along here. In fact, I'm looking at about 1 metric ton of stuff which went down the belt. Do you mind accounting for it? And you'll say, no, it wasn't there. It was never there. It was only pretend there because of the filter factor, which is a way of lying. And the accountant will say, yeah, that's very funny, but I'm looking at a metric ton of gold. Do you mind explaining where this metric ton of gold ore has disappeared to? And you can say, well, it disappeared onto the ground. It doesn't really exist. But accountants are idiots. And so we end up with this problem that, according to the computer, stuff went down a conveyor belt during this period. In reality, it didn't. So as soon as we're into sampling, we're into statistics. As soon as we're into statistics, we're into lying. If we then use filter factors, which is a smoothing way of smoothing sampling, then we're lying even further. Another thing to know about with ADCs and DACs is that they're expensive. They're expensive items, so the PLC manufacturers like to put in the cheapest ones they can. We talk about the resolution of an ADC or a DAC. The greater the resolution, the greater number of bits involved, the smoother it is. Because, of course, in the digital world, things actually work in steps. In the analog world, things work as a smooth line. The more bits, the smaller the steps. So that higher resolution ADCs with more bits have smoother steps. To give you an example, an 8-bit ADC or DAC, and I'll just put up there so you will remember, ADC is an analog to digital converter, and a DAC is a digital to analog converter. Okay, an 8-bit ADC. In 8 bits we can store the numbers 0 through to 255. What that means is, with an 8-bit ADC, if you were outputting, for instance, to a valve, you would see that valve stepping open in steps of about 0.4, about 0.5%. So if you were inputting from a temperature sensor, you would see, as the temperature went up, you would see the temperature jumping in half-degree increments, which isn't very accurate. If you want to read 12.12, you won't read 12.12. You'll read 12 and you'll read 12.4. And that's as accurate as you're going to get. With 12-bit ADCs, the increments are much, much smaller. They're 0.024. With 14-bit ADCs, the increments are much, much smaller still. With most PLC manufacturers nowadays, most PLC manufacturers, their ADCs will either be 12 or 14-bit. A lot of PLC manufacturers, their DACs are still 8 bits. What that means is that with most PLCs, output will step in steps of 0.5%. If you want to control your valve to 14.11%, you won't get it. It'll either go to 14% or 14.5%, and that's as good as it's going to get. So when you're looking at PLCs, the ADCs and the DACs for the inputs and the outputs of the analog values, the more bits, the more smoothly it will output. Of course, you can buy more smooth ADCs and DACs. You can buy higher resolution ADCs and DACs. But once again, it comes back to dollars. If you want to pay more money, you can buy smoother ADCs and DACs. But it's all down to cost. Now, there is a way of making a digital output look like an analog output, and that's by using a thing called pulsed width modulation, PWM, pulse width modulation. What this means is we have a thing called the duty cycle. Now this is showing this diagram is showing two duty cycles. There's one duty cycle here, and there's another duty cycle on the other side. What we do with the digital output is if we want 25%, we output for, at the moment I've got a duty cycle of 1 second. We output on for 0.25 of a second, so 1/4 of a second. So that's 1/4 of a second. So I have it on for 1/4 of a second, and I have it off for 3/4 of a second. And so on average, it's on for 1/4 of the time. So on average, the output is 25%. So what I've just done is I've taken a digital output and I'm using it to output 25% by duty cycling. Similarly, if I want 50%, I have it on for 1/2 a second and I have it off for 1/2 a second. And within every second, I switch it on for 1/2 a second and I switch it off for 1/2 a second. So using pulse width modulation, I can have percentages. I can use a DO, which normally only goes on or off, and I can have percentages. Now if I'm outputting to something, for instance, typically we output to heaters. If I'm outputting to a heater, which is a large chunk of metal, that heater will heat up 1/2 as much, because on average I'm sending it 1/2 as much electricity. So pulse width modulation allows me to turn a digital output into an analog output. With digital outputs, it should say digital there, with digital outputs, there are two different types of digital outputs. A typical relay contact output, which we call a volts-free contact. This consists of nothing more than a screw, a relay contact, and another screw. It's called a volts-free contact because the PLC doesn't supply any volts anywhere. All it supplies is a relay close. So a volts-free contact is a relay on the PLC board. Volts-free contacts are good for about 500,000 operations. And when they quote 500,000 operations, they're not mucking around. These things work for 500,003 operations and then they stop working. And every single relay on that board will stop working at the same time. Which means a situation I once had, I had a whole bunch of PLCs with a whole load of volts-free contacts, and they'd all done their 500,000 operations, and every single board broke down at the same weekend. So there's that type of digital output, which is the volts-free contact. There is another type of digital output which uses a silicon relay, if you like. It's called a triac. Now, I'm told by the electronics people that nowadays we use diacs. I'm not really interested in that. We still call them triacs. And what a triac is a silicon version of a relay. Now, with a triac, what we do is we have 24 volts on one side of it, and we switch it off. This is the on-off bit. We switch it on and off, and the 24 volts appears and disappears from the screw, which is the terminal. Now, when we're talking about digital outputs, if we're going to be digitally outputting to pulse width modulation, so we're switching on and off twice a second, what would be the better option? A volts-free relay contact or a triac output? Okay, let me tell you, the volts-free contact will last 500,000 operations, twice a second. The volts-free contacts will last 9 months, and then every single one will die. The triacs, in theory, will last forever. So you can use a volts-free, and I have used a volts-free in the past, but I prefer to use the triacs because, like I say, when the volts-free goes, 9 months after you install, every single one will fail on the same day. So I'm going to prefer to use the triac. Now, we have a slight problem with using the triac. Oops, going back. And the slight problem I have with the triac output, let me just draw one. I don't remember how it looks. Oh, yeah. Right. Here's the screw. Now, one slight hitch with the triac output is that the triac is a high impedance device. So if I come along to my triac output with my digital voltmeter, and I come along and I connect one side up, if my triac is off, how many volts would I see at my digital voltmeter? So when the triac is off, I see nothing at the digital voltmeter. Now, what I'm going to do is I'm going to turn my triac on, because I'm just so. There you go, I turn my triac on. When I turn my triac on, how many volts do I see in my digital voltmeter? "24 volts, yes. Okay, now I'm going to turn my triac back off again. How many volts do I see on my digital voltmeter? Yes, you're right. I will still see 24 volts. You see, because the triac is a high impedance device, there's nowhere for the volts to go. They can't leak backwards through the triac. They can't go through the DVM. So the volts just sit there. So you cannot test a triac off-load, because the volts will just sit there and it will just appear as if the voltage is there forever. You can only test a triac if you have a load attached to it, some kind of load. You can only test a triac on load, because then when you turn it off, the voltage disappears and goes to 0 volt. So a trap for young player is, if you have a triac output, never test it off load, because you'll turn it on and it'll appear that it's come on, and then you'll turn it off and it will appear that it stays on, and you will be fooled into thinking, oh my goodness, the triac's broken. But it's not. You have to test, you can only test triac outputs on load. Okay. The next thing is, if we're outputting from our output, our digital output, to a heater, we're typically going through a contactor. Now, I'm not going to use a contactor, because if I switch a contactor twice a second, it's going to be stuffed within a week. So what I'm going to do instead is I'm going to use a solid-state relay. A solid-state relay, to all intents and purposes, is a silicon contactor. It's a contactor with no moving parts. It's really a great big transistor. So it's a contactor with no moving parts. Now, has any of you seen solid-state relays before, or installed solid-state relays? Well, a couple of things you must know about solid-state relays. Firstly, a solid-state relay can fail in either mode. What that means is it can fail on. 50% of the time they fail on. Now, if we're outputting to something like a heater, you don't want a heater to come on permanently. So there's particular rules that apply to solid-state relays, and we have to be careful with the safety of them. The second thing about a solid-state relay is it's a high impedance device. It will switch on if you have anything above 3 volts, this one, and this one will switch off, sorry, anything between 3 volts and 32 volts will switch this thing on. Now, when we wire it, if we're wiring to a heater, for safety, regulations state that on the load side, we have to have isolation on the load side. You're not allowed to have isolation on the control side, because if it fails, it can just as easily fail on. So you have the isolation on the load side, and also if you're outputting to a heater, there have to be 2 thermal overloads on the load side of things. And those thermal overloads are designed so that when the thing fails on and the heater catches fire, the thermal overloads will trip it out. Now, on the signal side of it, because it's a high impedance device, we have to have a resistor. If we don't have a resistor, what's going to happen is it's going to switch on, and 24 volts will appear at this point here, which will switch it on. If you don't have a resistor in place, when you switch it off, the 24 volts doesn't have anywhere to go to. So the 24 volts will just sit there and the thing will stay on. So you have to have a resistor to supply a ground route. It gives it a drain, a direction of an ability to drain to earth. If you don't have a resistor, it will turn on and never switch off. The value of the resistor depends on the duty cycle, because what you must make sure of is the duty cycle will switch it on and then it will slowly drain away. You have to make sure that it drains away fast enough so that when the next duty cycle comes along, it's actually switched off. Now it switches off at 3 volts, so you have to make sure that you have a resistor that is such a size that it switches off at 3 volts. It reaches 3 volts before the next duty cycle comes along. However, you can't have too small a resistor, because if you have too small a resistor, the voltage may never build up to 3 volts. You have to make sure that you've got a resistor that's big enough so that the voltage will reach 3 volts in order to switch the thing on. So when you get your solid-state relay out of a packet, there's a little piece of paper with it. And that little piece of paper, I know traditionally we throw away any piece of paper or instructions immediately, but that little piece of paper will tell us what size resistor we should put on our solid-state relay so that it has a drain path and it will be able to switch off quickly enough. So using solid-state relays, we can control heating circuits. We can also use them to control things like lighting circuits and that sort of thing, so that we can output from a DO and we can get an analog value.